Hello, my name is Aida Hashamlu, and today I'm going to talk about my project, which was clustering handwritten digits using k-means algorithm. Handwritten digit recognition plays a crucial role in various fields such as optical character recognition, document processing, and even digitizing historical archives. The use of k-means clustering, a popular unsupervised learning algorithm, offers an effective approach to group similar handwritten digits together based on their shared characteristics. In this presentation, we will go over the application of k-means clustering on the MNIST dataset of handwritten digits. For educational purposes, I ignored the existing labeling information in the dataset and relied solely on k-means unsupervised capabilities for segmentation. We will see why and how PCA dimensionality reduction technique is used to reduce the feature space. We will go over the methods to determine the optimal number for clusters. We will then analyze the resulting clusters, visualize their centroids, and assess the quality of the clustering solution using evaluation metrics. Finally, we'll have a brief review on similar works already done with this method and the plan for future advancements in the digit recognition. What is MNIST database? The MNIST database, which stands for Modified National Institute of Standards and Technology Database, is a large database of handwritten digits that is commonly used for training various image processing systems. It was created by remixing the samples from NIST original datasets, which was taken its samples from American Census Bureau employees and American high school students. The black and white images from NIST were normalized and centered to fit into a 28 by 28 pixel bounding box and are anti-aliased, which introduced grayscale levels. In this work, I have used the MNIST dataset provided by Keras module from TensorFlow library, which is already vectorized and is in NumPy format. Why PCA? How I used it. I used PCA to reduce the dimensionality of the dataset and computational complexity during running k-means, while maintaining the main patterns. To determine the number of components for PCA, I used explained variance ratio and cumulative explained variance. By plotting out the results, I could see how much information is retained by each principal component and make an informed decision about the number of components to keep. Explained variance ratio represents the proportion of the dataset's variance explained by each principal component. Cumulative explained variance shows the proportion of total variance explained by a given number of components. After plotting the results from these two PCA component selection methods, I picked a value of 100. Although we should bear in mind that PCA component number selection is a trade-off between dimensionality reduction and the amount of information retained. Why k-means algorithm? K-means is used as a common method for handwritten digit segmentation. When combined with other classification techniques, k-means can help improve feature representations and cluster grouping. K-means is an unsupervised learning algorithm, which means it can find patterns in data without needing pre-existing labels. The cluster centroids found by k-means can be used for classification. The labeling rule is straightforward. Find the closest centroid and assign the new instance to that cluster. K-means is relatively simple to implement and scales to large datasets. In case of following an ensemble approach, all the cluster data can be labeled by assigning the instances to the closest cluster, preparing the dataset for training a classifier. Finding the optimal k value. Before starting, I set the maximum number of k to 30 to avoid overfitting. Also, instead of running k-means while benchmarking, I used mini-batch k-means, which is a variant of the k-means algorithm, but it uses randomly sampled subsets of the input data called mini-batches to reduce the computation time. The first method I used was the brute force. I applied the k-means algorithm multiple times with different values of k. I plotted the gain accuracy for each and compared the clustering performance for each value. Second method that I used was the elbow method. In elbow method, the inertia measures the sum of square distances between each data point and its closest centroid. By plotting the corresponding inertia values for each k value, I could identify the spot where the rate of decrease in inertia begins to level off and forms an elbow shape in the plot. The third method I used was the silhouette score. The silhouette score quantifies the quality of clustering by measuring the cohesion and separation of data points within clusters. The value of k that maximizes the silhouette score is considered the optimal number of clusters. For the two methods above, I also integrated K-Elbow Visualizer module from Yellow Brick library to gain more insight about the results. The fourth method I used was gap statistics. Gap statistics compares the within cluster dispersion of the observed data with the expected dispersion on their null reference distributions. It identifies the k value at which the gap reaches its maximum. The optimal k corresponds to the point where adding an additional cluster does not significantly improve the clustering result compared to the null reference distribution. And finally, the results. I applied k-means clustering with k equal to 10 and evaluated the clustering performance using accuracy, adjusted rand index or ARI, and normalized mutual information or NMI on the test set. The accuracy rate was 60%, indicating that 60% of the data points were assigned to the correct clusters based on the true labels in the test set. ARI measures the agreement between the true labels and the cluster assignments, with a score of 0 indicating random labeling and 1 indicating a perfect cluster assignment. NMI measures the mutual information between the true labels and the cluster assignments, with higher values indicating better agreement. ARI score of 0.38 and NMI score of 0.5 in my case indicated that there is some degree of agreement between the clustering results and the true labels. However, there is room for improvement. A learned lesson here is that while k-means is a popular clustering algorithm, it may not be the best choice for every problem. It's worth considering alternative clustering algorithms or incorporating additional techniques to enhance the clustering performance. Now we'll review some works done by other researchers. Monsarif et al. In the handwriting of image segmentation using the k-means clustering algorithm with contrast stretching and histogram equalization started with data acquisition. Then they applied contrast stretching and histogram equalization on scanned images, followed by k-means clustering algorithm. The results showed very good accuracy. Boyang Lee, in an experiment of k-means initialization strategies on handwritten digits dataset, evaluated the performance of three classical k-means initialization strategies on UCI-ML handwritten digits dataset: random, k-means plus plus, and PCA-based k-means. The experiment results showed that the three k-means initialization strategies find almost identical cluster centroids and they have similar accuracy of clustering. However, PCA-based k-means strategy significantly improves running time. Anthony S. Maida et al. In an efficient character recognition scheme based on k-means clustering proposed using LDA analysis followed by a Bayesian discriminator function to cluster the data into semi-Gaussian subclasses. Then PCA and k-means clustering were applied. The results on the MNIST dataset displayed great improvement in accuracy. What's next? The next steps on this project would be refining cluster boundaries. As results showed, there is some overlap in boundaries between clusters. To fix that, I'll apply post-processing techniques like fuzzy clustering, fuzzy c-means, or soft clustering to assign data points to multiple clusters with varying degrees of membership. Another way is ensemble clustering, which is applying ensemble clustering techniques such as consensus clustering or cluster aggregation. These methods combine the results of multiple clustering runs to generate a more robust and stable clustering solution. Ensemble clustering can help mitigate the impact of the random initialization and improves the overall clustering quality. Another step would be evaluation of alternative clustering algorithms. K-means may not always be the best choice for every dataset. I will explore alternative clustering algorithms such as hierarchical clustering, dbScan, or Gaussian mixture models. I'll then evaluate their performance and compare them to the results obtained with k-means to determine if alternative algorithms yield better clustering results. Thank you.